In 4.3, we look at subspaces, and a subspace is basically a subset of a vector space that is also a vector space. Now, keep in mind, not every subset of a vector space is also a vector space. For example, R2 is a vector space. If we look at all vectors, all two-dimensional vectors, where x and y are any real numbers, that makes up a vector space, and we looked at that in section 2. If you add any two-dimensional vectors together, you get something that's also a two-dimensional vector. If you change the order that you add them in, that's fine. It's commutative. The opposite of this exists if x and y can be any real number. There is a zero vector if x and y can be any real number. We can multiply that by any scalar and get something that's also in R2 is a two-dimensional vector. So R2 we know is a vector space. So let's just say our vector space is R2. And if we consider the first quadrant vectors, first quadrant vectors in 2 dimensions, that's a subset of V, but in this case, x and y have to be greater than or equal to 0. If you think about quadrant 1, 2, 3, 4, if we're in the first quadrant, then the x and y components are both positive. But notice this is not a vector space. It's a subset of R2. If we think about this being the set of V, then this is a portion of those, but it's not an actual vector space. If we think of taking a scalar times something that is in this subset, if x and y are both required to be positive, then when we multiply that by a negative scalar, we get something that's negative, so it's outside this subset. So we think about it, if this is, let's call that W. So W is a set of first quadrant vectors. Then if we multiply one of those by negative, we get something that's still a real number, but it's not inside that set W anymore. So therefore, this is not a vector space. So it turns out it's fairly easy to determine if something is a subspace. We just have to meet 2 criteria. If it's if we know that V is a vector space, and W is a subset of V, then let's consider U and we'll say little v. So this big V, that's our vector space. This big W is our subset of V, and U and V are in the subset. If U plus V is in W, so if we're closed under addition, you add something in W plus something else in W and get something in W. And if we take some scalar times any vector in W and get something that's in W, then W is not only a subset, W is a subspace of V. So it's a vector space, which is a subset of a bigger space, so we call that a subspace of the overall space. But that's a lot easier. If we know that it's part of a vector space, then we only have to check these two criteria to see if it meets those. So let's go through, let's look at a couple examples and see whether these are subspaces or not subspaces. Let's see. They give some examples in the book. We'll do one of them. So let's look. Let's say V is the set of all 2 by 2 matrices. And let's show that W is all, which is all singular 2 by 2 matrices. So if V is all 2 by 2 and then W is all the singular ones, then think of V as being your space, which we demonstrated in the last section that is a vector space. If we look at a subspace of that, which is just a set of singular, I say, let me be careful, not subspace. If we look at a subset of V, so this is V, this is W, we want to see, is this subset also of a space? So it turns out that it's not. If we look at a singular matrix, let's call this A. Remember, a matrix is singular if you take the determinant of it and get 0. Or if it's not invertible. Let's look at B, and let's let B be, we can pick lots of different ones. For example, this is singular. Notice the determinant of that is 0. If you were to add these two together, we would get 1, 0, 0, 1. If you take the determinant of that, you get 1 minus 0. Notice that does not equal 0. So A plus B is non-singular. So if W is singular, A plus B, so A is something in W, B is something else in W, you add those together and you get something that's still a 2 by 2 matrix, but it's not in W. So W is not a subspace of V. It's a subset, but it's not a subspace. And that's what we're looking for. We're looking to determine if something is a subspace. Let's see. Let's look at W is the set of vectors that not vector is vectors in R2. So R2 is a vector space. W is a subset of that, where the second component is 1. So a two-dimensional vector, the first number can be anything, the second number is 1. So R2 is a set of all possible vectors, or you could think about those as ordered pairs, W is a subset of that. It's all of the ones where the y component or the second component is 1. Now this violates both of our conditions to be a subspace. For example, if we take and multiply by a scalar, we get 2x by 2, which violates that the second component is a 1. So if we think about this in terms of this being everything in R2, and then W being a subset out of that, all the ones where the second element is 1. So we picked a random point, x1. If we double that, we get a point that's not in W. It's still a two-dimensional vector, but it's a point that's outside of W. And W is not a subspace. So let's see, what's another one we could look at? Let me pause just for a second. This one would be pretty easy to illustrate that it's not a vector space. Let's say V is R3, so X, Y, Z. Let's show that W, which is the set of Pythagorean triples, A squared plus B squared must equal C squared. So W is made up of the sets of ordered triples such that A squared plus B squared is C squared. So our R3, that's all three-dimensional vectors. W, that's just a little sample of those such that we take the first component squared plus the second component squared, it gives us the third component squared. For example, 3 squared plus 4 squared is 5 squared. 9 plus 16 is 25. So 3, 4, 5, that's a Pythagorean triple. Let's see. 5, 12, 13 is another Pythagorean triple. 5 squared plus 12 squared is 13 squared. So 5, 12, 13, another Pythagorean triple. But notice this violates both principles. It violates that if we add these together, that it's still in W. If we add these two vectors together, we get 8, 16, 18. And let's just real quickly show 8 squared is 64, 16 squared is 256, plus 18 squared, I'm drawing a blank off the top of my head, 324, and that's not true. Those things are not equal to each other. 64 plus 256, just make sure, yeah, 16 is 256, plus 64, that's 320, not 324. So we took 3, 4, 5, which is in W, 5, 12, 13, which is also in W, and that gave us 8, 16, 18 when we added them together, which is not in W. So if that's not a closed set, when we add points together, then this is not a subspace. So it turns out if we can relate something to, if we have a description and we know something that's related to it, it's a subspace of. So when we look at two-dimensional or 2x2 matrices, and we have some specific definition, instead of having to prove or verify that they abide by all 10 of our axioms, I can't count, instead of proving that our set abides by all 10 axioms, we know that if it's a 2x2, that's a subset of mth2, which we know that mth2 is a vector space. So since W is a subset of M, all we have to do is verify whether or not W holds to, oh, I'm going the wrong way, to these two principles. If W holds to those two principles and it's a subset of M22, then it's also a vector space because it's a subspace of M22. So instead of having to verify 10 different axioms, we have to do 2, which of course that's much, much easier. Mention one more thing for right now. I'm not going to work an example of it at the moment, but something that might be useful in some of our homework problems. This is theorem 4.6. If we have some vector space U, so U is our vector space, and let's say that V and W are subspaces of U. So V and W. So U, V, W. So if V is a subspace and W is a subspace, then their intersection also is a subspace of U. So again, V is a subset of U, W is a subset of U, they're a subspace, V is a subspace, W is a subspace, therefore it turns out their intersection is also a subspace. So without going into any more detail than that, we might come across that in homework or we might not.